Now, of course, arctangent isn't the only inverse trig function out there. There are others that we want to think about integrals related to them as well. So let's take a look here at this example 4, where we have the integral from 0 to the square root of 3 over 2 of the function 1 over root 3 minus x squared. So we maybe notice that this looks similar to the integral formula which we have, which says that the integral of 1 over root 1 minus x squared dx equals arc sine of x plus c. So here the primary difference is whether or not we have this 1 or this 3 as the constant term here. And we're going to deal with this 3 the same way that we dealt with in example number 2, the same way that we dealt with this 4. We're going to factor it out of the denominator, and we're going to then pull it out of the integral. So here what we want to do is we want to say, okay, well, let's factor that 3 out first. So this is going to be the integral from 0 to root 3 over 2 of 1 over square root of, let's see, 3 times 1 minus x squared over 3. Then I can I can break up the square root into 2 different pieces. So this is 0 to root 3 over 2 of 1 over root 3 times the square root of 1 minus x squared over 3. It's important to note here that I can break up this square root because we're multiplying 3 and 1 minus x squared over 3. I can't, for instance, break up this square root into the square root of 1 and the square root of x squared over 3. It doesn't work that way for addition or subtraction. Square roots do behave nicely with addition, however. So with that said, we can go ahead and we can continue to factor this square root of 3 out of the integral. So we've got 1 over root 3. And we can recognize that this x squared minus 3 quantity, we can realize it as x over the square root of 3 squared dx. Again, we're realizing it this way in order to get something squared here, and whatever is squared, we're going to let that be u, so that we can get a formula which looks very similar to our arc sine integral formula here. So now that we know what u should be, let's go ahead and work through that substitution. So we want u to be x over the square root of 3, which is to say that the du times the square root of 3 equals dx. And so let's see. So we can now go ahead and do this substitution. Oops, I forgot my limits of integration last time. Root 3 over 2. Great. So we still have this 1 over root 3 hanging around out front. We have this integral here. Now what I want to do is I want to replace my bounds of integration, so the limits of integration, the 0 and the root 3 over 2, in terms of their u values, because I'm changing variables to u here. So if x equals 0, then u is also going to be 0, because 0 over the square root of 3 is 0. And if x equals root 3 over 2, then u is going to be root 3 over 2 divided by root 3, in other words, 1/2. So my bounds of integration here go from being 0 to root 3 over 2 to being 0 to 1/2. I have 1 over square root of 1 minus, I've let x over root 3, that is what I've designed to be u, so this is u squared. Dx, we just said, was root 3 du. And now we notice that this root 3 is actually going to cancel out with the 1 over root 3 that we had earlier. So that works out pretty conveniently for us. And we are now able to actually do this integral. This is the exact formula that we have for arc sine here. And so we can say that this is arc sine of u, evaluated from 0 to 1/2. So this is arc sine of 1/2 minus arc sine of 0. Brief refresher on how the arc sine function works so we can find the absolute value here. Arc sine takes in y values on the unit circle and outputs angles between minus pi over 2 and positive pi over 2. So I want to think about which of the points on the right half of the unit circle here have a y value equal to 1/2. And that point is right here. It's the point √3/2, 1/2. And the angle that corresponds to this is the angle pi over 6. So arc sine of 1/2 is the angle pi over 6. Arc sine of 0, I want to think about which of the points on this unit circle here has y coordinate 0. And that is this point here, the point 1, 0. And so arc sine of 0 is the angle corresponding to 1, 0 here, and that is the angle 0. So in the end, this all works out to be pi over 6. So perhaps not a number that you would have expected to show up based on the starting integral that we had. So certainly it doesn't maybe seem obvious that pi should be showing up when we're integrating just something involving a square root and a 3 and an x squared. But magically it does. So we get kind of a nice answer out here from a fairly complicated looking integral. All right, so that was one integral involving arc sine. We also maybe want to think about, maybe you've had this question, why don't we have an integral formula of the form integral of something equals arc cosine? We have one for arc tangent, we have one for arc secant, and we have one for arc sine, but we don't have one for arc cosine. Sort of the question is, why not? And the answer is that we could, so for instance, the way that we would come up with such a formula is we would want to find out, well, what's the derivative of arc cosine? Because the integral of arc cosine's derivative should be arc cosine. So the derivative of arc cosine we know to be -1 over the square root of 1 minus x squared. So our integral formula could look something like integral of -1 over root 1 minus x squared dx equals arc cos of x plus c. But maybe rather than memorizing that this this integrand here, its integral is arc cosine, we have a better way of dealing with this. Notice that this integrand looks a lot like the integrand for arc sine. In fact, the only difference is a negative sign in the numerator there. So the way that we prefer to handle this is by factoring that negative sign out, square root of 1 minus x squared dx, and realizing this as minus arc sine of x plus c. So what this really tells us here, if we kind of work through this chain of equalities, is that this minus arc sine of x plus c is the same as arc cosine of x plus maybe some other c. So minus arc sine and arc cosine end up differing only by a constant, and if you graph both of them, you'll find out you'll see why that is.